All right. So today we're going to keep talking about our sequences, and we're going to actually look at some rate of change. But we're going to go back to yesterday's assignment that you guys were given, and we're going to look at problem 83 real quick. So on problem 83, they gave us t of 1 equaled 12, and then they said t of n plus 1 equals t of n minus 5. So this is actually written in the recursive formula. So under the recursive, or under the recursive sequence, they give you one of the terms, and then they tell you how to figure out the next term, right? So if we wanted to, we could actually turn this into a little table where n is the term number that we're looking at, and t of n is what that number is in the actual sequence, right? So if we wanted to find our first term in the sequence, well, what's our n right here? 1. So that's telling us it's the first term. And what is our first term in the sequence? 12. So we know our first term is 12. And I think they wanted us to find the first 5, right? So now that we know the first term in the sequence, we got to try and figure out how to figure out the next term in the sequence. And that's where this little guy comes into play. Right? So if we wanted to figure out the second sequence, t of n, that would be our first sequence, right? And then we're going to subtract 5. So like technically you would be doing t of 1 plus 1 equals t of 1 minus 5. So t of 2 is going to equal, what was t1? 12 minus 5. And what's 12 minus 5? 7. Right? So if you don't want to go through and actually use that recursive formula every time, could you figure out the third term? What are we doing to figure out the third term? What do we do to get from here to here? Subtracted 5. So what are we going to do to go from here to here? Subtract 5 and we get 2. Yep. And then to get to the fourth term, we have to subtract 5. So what's 2 minus 5? Negative 3. Yep, good job. And then we have to subtract 5 again to get to the fifth term. So negative 3 minus 5 is negative 8. Right? So that's how recursive formulas work. How many of you guys were able to squeeze out that problem on your own? All right. So you're ready to move on to our next little topic, next little section? So we're still in Appendix A. Now we're going to go to Section 3 and then that Topic 1, and we're going to talk about rate of change. And we've kind of heard the words rate of change, and sometimes we use different words instead of rate of change. If we're looking at a line and we're talking about the rate of change, like how to get from one point to the next point, we're talking about the slope. Good job, absolutely, right? So in a linear equation, we're talking about that slope, right? So we're going to look at 3 different sequences, and we're going to see if we can find that rate of change on how we get from one number to the next in the sequence. And when we can figure out how we get from one number to the next, we can then sit there and classify it as arithmetic, or we can classify it as geometric, or we can classify it as neither. And then we're going to sit there and see if we can kind of come up with a pattern, and then being able to figure out if our sequence is linear, quadratic, or exponential based off of the rate of change. All right, so you ready for the first sequence? So I'm going to give it to you guys in a table form. So n is our term, and the number, and then t of n is the actual term that's in the sequence. So we're just going to look at 4 terms, and we're going to go with 27, 54, 81, and 108. And if you guys want to, you can check this out in your CPM textbook, your online textbook. This is problem number 84 in the textbook. So now that we have our sequence, we want to look at our sequence and be like, how did they go from one number to the next number? Anybody have any ideas on how we could go from 27 to 54? Add 27? Yep, good job. And how can we go from 54 to 81? Add 27, good job. And from 81 to 108? Add 27. Very nice, right? So that rate of change or we even refer to it as that common difference, is what? Whoop, how did I go to that? It's 27. Right? And if you want, you could even put a little positive in front of it if it makes you warm and fuzzy inside. So our rate of change is constant though, right? When we go from one number to the next, it's always plus 27. So because it's that constant rate of change, and it's that 27, we know then that it's going to be a linear sequence. And because it's plus 27, we're adding to get from one term to the next. We know it's a what kind of sequence? Arithmetic sequence, yeah? Right. And then last but not least, we could actually come up with our equation for this. So yesterday in the notes in the video, instead of writing it as y equals mx plus b, we use that sequence notation. So we had t of n equals c, the common difference, n, the term number, plus a sub 0, which was that 0 term. Right? And really it's the same thing as slope-intercept, right? That common difference, which is that rate of change, is going to be your slope. N would have been your x, and y equals mx plus b, right? It's your input here. And then a sub 0, which is going to be our 0 term, well, that's going to be the same thing as your y-intercept, right? Because that's when that x is 0 or when the n is 0, so that's where it would be crossing the axes. So then now we can write our little function. So we would have what? T of n equals, what's our common difference? 27, right? N is the term, so depending on what number we want to know in the sequence, plus a sub 0. So we have to find the 0 term, and we only have the first term, so how would we go back to get the 0 term? What's t of n going to be? If you're adding 27 to go down the sequence, you'd go back. So, yep, so it'd be 0, right? So A sub 0 would actually be 0 in this one. So if we just wanted to clean it up, it would just be 27n. Okay. And if I wanted to figure out the 10th term, instead of making that table and keep going all the way down until I get to the 10th term, I could just put 10 in for n and get 270. Okay. So let's see what information we get to gather from all of this, right? So off of that little table, we were able to find that rate of change, or that common difference of being plus 27, right? Because that rate of change was consistent, it was constant, we knew that it was going to be linear, because we were adding 27 to each one. Because it was addition, we knew that it was arithmetic, and we were able to come up with an equation. Not too shabby. All right. Ready to try another sequence? 2 of the 3. All right. So again, we got, we have our n and our t of n. Right? No different than if these were x's and y's. N would always be your input. T of n would be your output. And we'll just do, whoops, I'm going to leave a little bit of room just to go back. Yep. 4 terms. And let's go with a 9, a 36, an 81, and a 144. So to get from 9 to 36, we could add 27 onto that. Yeah. Multiply by 4. Yep, so if I multiply this by 4, I get 36. Right? What's 36 times 4? Yeah, that's actually 144. Right? I'm going to give you guys a little side note. This is really actually cool. Watch this. We'll get to this later, but got to show you now. Going from here to here, you know how this would be adding 27? To get from 36 to 81, I would be adding 45. And getting from 81 to 144, I actually add 63 onto those. So we know it's not arithmetic because they're not all constant, but this is crazy. I'm going to blow your mind. You ready? To get from 27 to 45, I add 18. To get from 45 to 63, guess what I do? I add 18. So when it comes to figuring out this equation a little bit, because it took you 2 steps to get to where you had that common difference, it means it's going to be a square. Isn't that crazy? If these didn't match and you went another time and then they finally ended up being where they were all the same, then you know that it's a 3rd degree. If it takes you 4 rows, then it's a 4th degree. Isn't that crazy? Isn't that pretty neat? All right. So that was just my little side note for you guys. Because math is cool. All right. So now let's see if we can figure out what's going on, how we're getting from one number to the next. Okay? So I know we were talking, you were just said where to get to like 36, you could do 9 times 4, right? If we kept looking at our 9s, what would we multiply 9 by to get to 81? 9. What do you think you got to multiply 9 by to get to 144?
3.
A little higher. A little higher. A little higher. 16. Okay. And if I keep those 9s consistent, what would I multiply 9 by to get 9? I'd multiply by 1, right? So we kind of have that consistency of that 9 going through, but then we're multiplying by 1, then we're multiplying by 4, then we're multiplying by 9, and we're multiplying by 16. So we want to be able to look at this 1, 4, 9, and 16 and see if we can come up with an idea or a pattern. Yeah. Is there a connection between this guy and this guy? Is there a connection between this guy and this guy? Is there a connection between, whoop, make my little circles go away. This guy and this guy? Yeah. So what am I doing to my n term? I'm squaring it. Yep. Right, this would have been 9 times 1 squared, right? This is 9 times 2 squared, 9 times 3 squared, right? 9 times 4 squared. So if I wanted to keep going, right, and I want to get down to my nth term, what's my equation going to be? I got my 9, right? And then what am I going to times it by? N squared. Yep, awesome. So we just want to make sure that we write it as a sequence. Ooh, what happened there? So to write it as a sequence, we would have t of n, right, equals 9n squared. Didn't I tell you it was going to be a square? Look at that. I knew what I was talking about for once. Aren't you proud of me? All right. So since it is a square, we can actually put it into a family of functions. We can call this a quadratic, right? We know that if our variable, the highest variable, has a square on there, it's going to be quadratic. We're not multiplying by a common factor, right? We're not multiplying by one number to go from one to the next, right? We're not multiplying by 3, we're not multiplying by 5. Our n is actually what's being squared. So it's not going to be arithmetic because we're not adding by a common term, and we're not multiplying by a common term, so it can't be geometric. So this one isn't arithmetic and it isn't geometric. So when it comes to quadratics, we know that they're going to be a neither. Right? Inputs are known as domains, right? But we know that these are all of our inputs. These are all of our domains. Right? These are all of our, starts with an O, outputs. So those are all of our range values. Okay? All right, let's use some foreshadowing. What's coming up next? No, we had arithmetic. We had a neither. Geometric. Let's see if we can figure out an old geometric one. Give you a nice little table again. N and T of n. 1, 2, 3, 4. We're going to go with a 6, a 12, a 24, and a 48. So can we add a common difference to get from one to the next? No. What are we going to do? We're going to multiply by 2. We're going to multiply by 2. And we're going to multiply by 2. Right? So because we know that we're multiplying to get from one term to the next, we know that it is geometric. Okay. So now we just need to kind of figure out, trying to work on coming up with that equation, right? So, whoops. I'm going to go back to my 0 term. So if I'm multiplying by 2 to get from one term to the next, I'm going to divide by 2. So my 0 term is going to be 3, right? So to try and come up with my equation, I kind of want to start with this 3, right? So this guy got a 3. Now I don't know what I'm going to do to a 3. I'm going to times it by 1, I guess, or something. Who knows, right? So now, keeping my consistent with my 3, what do I do with my 3 to get to 6? Multiply by 2, right? So then to get to 12, I still have my 3. I'm going to keep that 2, and then I'm going to multiply by another 2. My 24, I started with 3, and then I had multiplied by 2, I multiplied by 2, and then I'm going to multiply by another 2. Starting to pick up a pattern here. I had 3 times 2 times 2 times 2. That gave me my 24. And then what did I do to 24? I times it by 2. Right? Huh. So this one gives me like 3 times 2. This one would be 3 times 2 squared. Okay. This one would be 3 times 2 to the third. I should have done these in different colors. I'm going back. I think these babies are running together, aren't they? So this one's 3 times 2. This one's 3 times 2 squared. Now we have what? 3 times 2 to the third. This one's going to give me 3 times 2 to the fourth. So if I wanted to keep going and get down to like my nth term, where's my n going to go? What's the piece that's changing? Is the exponent the piece that's changing? Can we link our exponent to anything on our table? Anything else a 1? Yeah. We got a 3. Does that show up anywhere else on this one? 3. So if we're looking for our fourth term, our exponent's going to be 4. So if we wanted to find the nth term, we'd have what? 3 times 2 to the nth, right? Writing it like a sequence, we just got to get our t of n in there. T of n equals 3 times 2 to the nth. Anybody remember what family of functions this is when your variable is in the exponent? Starts with an E. Exponentials. Yeah. So if we have a geometric sequence, right, we know that it's going to be exponential, right? And you guys remember how to graph exponentials? Right. Alrighty. So today, you guys got a couple problems to work on. On 87, they give you 4 sequences. And then you just need to tell me if it's going to be linear, geometric, or neither. or sorry, let me rephrase that. If it's going to be linear, exponential, or quadratic, right? Because those are your family of functions. And then after you figure those out, then you're just giving me that common difference or that rate of change. What did you do to get from one term to the next term? So you either multiplied by a half, or you added a -6 to it, something along that lines. 88, solving that system of equations. You can do that by substitution, or you can get them both into linear lines and you can graph them and find where they intersect. 89 is finding the first 5 terms in the sequence. So it actually looks a lot like number 83, that same process that we used for 83. Number 90, they gave you a graph with some plots on it and they just want you to talk about it. What do you see? What do you notice? Like, tell me the story of what you see off of those plots. 91 is finding the parallel line. How do you know when lines are parallel? I give you 2 equations of a line. How do you know they're parallel? They have the same slope. Yep. And then 92, you're coming up with the equation of a line. They're going to give you the slope and a point, and you got to come up with the equation. They're going to give you 2 points, and you need to come up with the equation. They're going to give you a table, and a table is just an array of points, or coordinate points. So then you're going to come up with an equation, and then they give you a graph for you to come up with an equation.